Our next shorter talk before a little bit of a break is from Dr. Christine Baes, who's a professor of genetics in the Department of Animal Biosciences and the acting Associate Dean of External Relations for OAC. Christine's well known to many of you as an extremely productive dairy and occasionally turkey geneticist, but today she's going to share some of her team's work on the genetics of health and fertility. Christine, all yours.
Thanks, Stephen, and thanks, Mike, for leaving me 15 minutes to give a 30-minute talk. So there's that, right? Okay, so, and thanks, Stephen, also for limiting me to genetics of health and fertility, because you all know I'd love to talk about feed efficiency and methane, but I'm apparently not allowed to. So let's get right into it. How many of you here in the room believe that there is a genetic component to health traits? Okay, how many don't believe that? Come on, be brave. I hear you saying it, but you don't actually ever say it in front of other people. What about fertility? Our veterinarian friends over here, how many don't believe that genetics has something to do with it? Oh, okay, here he's admitting, okay, so a little bit, right? These are difficult traits from a geneticist standpoint. They are complex, they're multifactorial, they have low heritabilities, they're hard to measure, and they do make genetic progress quite difficult compared to traits like milk production, etc. And I think we need to start back at the very beginning of what we can measure. So how many physiologists in the room? Nobody? Honestly? Guys, come on. We're getting your stretches. Okay. I'm going to talk about reproduction traits. Oh, there's Eddie. Hey, Eddie, how's it going? What are reproduction traits to a geneticist? Okay, so this is different to a physiologist. Let's look at this for a minute, all right? We have a heifer. Everybody knows what a heifer is, right? So AI, not artificial intelligence, not avian influenza, artificial insemination, boom, and that is a trait, okay? That's age at first service. That's what we use. Then we move on. We might breed them again if they don't catch, right? And then all of a sudden, day 56 happens, and we say, okay, this is non-return rate, and they get a 0 or a 1. Okay? Then we might breed them again, and at some point, there's a birth, right? And this trait here, first service to conception, is another trait for us. Now, any physiologist would already have kittens about this because it's not exactly biological, right? So anyway, it doesn't matter though, right? We're geneticists, it's okay, we can only count to like 5. So here's a calf, right? Birth, great, everybody parties. Then that animal becomes a cow. We have again calving to first service, right? Then we have again another AI, another insemination, non-return rate, right? Difference between the first breeding to when the 56th day comes. And then we have first service to conception, because here we have a successful AI, and then there's another calf. This is reproduction to a geneticist, because that's all we write down. Just to start with that, okay? So how are you supposed to fix that, right? How are you supposed to work on that? Let's look at some trends, right? Geneticists love to look at trends here. So we're looking here on the y-axis, we have calving to first service to conception, and days open here. And we have calving interval in days on the secondary y-axis. And we can see that days open over time, and this is old because this is trends, right? We're looking at a days open of 125 days down to 114 days. That's good. Calving to first service also down by 10 days. Calving interval, don't be confused. This isn't any more than 10 days because you have to look at the secondary axis. But overall, all we see is a difference of 10 days. Right? And when we look at something like first service to conception, which is actually a pretty important trait, we only see a difference of a day over 10 years. Now, these are genetic trends, and we started to wonder, why is this, right? I'm a geneticist. I love big graphs that show like fantastic things moving around and like, look at all the progress we've made. And we look at this and it gets pretty frustrating because one day isn't, like 2 would be better, 3 maybe, right? Like 1 is really not enough. So we started to think, right? And we had some ideas. And I talked with a bunch of colleagues and I said, okay, what could be wrong here? And the first idea was, okay, maybe the trait definitions that we're using as geneticists are too far from the biology or physiology of the actual cow. It's possible. Number two, management of reproductive performance could make bad cows look good. Another possibility. Then, you talk to the sort of more alternative people and they say, you geneticists, you're inbreeding everybody. You're just using the same bulls all the time. So, okay, it's a long shot. Inbreeding depression might have an effect on cow fertility. We'll check it out, right? And then I talked to my friend Rupert. Anybody know Rupert Brookmeyer in Switzerland? He's hilarious. Mike and him have a love-hate relationship. But Rupert told me, you geneticists are breeding for short teats. And as a physiologist, that's screwing up all of the fertility of these cows. So I said, Rupert, you know what? We're going to check this out. Thanks for that idea. We checked it out. Lucas Alcantara and Gerson Oliveira, they did this fantastic work. They created this beautiful shiny app, and you can actually go to it and check out all the correlations between all the traits that are collected in Canada, and you can map them out across from one another. So we checked out all of these fertility traits, and we looked at their correlations to teat length. Can you see the one row that has like almost no correlation here? That's teat length. Okay, so Rupert, as great of a physiologist as he is, right, this is not maybe the reason that we are seeing this problem. Maybe we did it wrong, but I don't think we did. So, next question, the inbreeding aspect. This is work done by Baes Macagnola together with Christian Malteca from our friends from North Carolina State University. We too collaborate sometimes, but only with people who we like. So again, we looked at pedigree inbreeding, so just inbreeding that we can take out of a pedigree, and we looked at FROH, that's pedigree, that's inbreeding that's estimated through genomic data. And we can say age at first service, number of services, non-return rate, first service to conception. They're a little bit lower, but also nothing that would, like the more inbreeding you have, maybe they have a little bit of an effect there, but nothing to write home about. Like this isn't what's causing our differences here. And also the monetary genetic gain that we can attain through genomic selection still far outweighs the detrimental effect of any kind of homozygosity that we're seeing there. So that's probably maybe a little bit, but not really it. Then Gerson did something pretty cool. He did a simulation. He looked at the effects of unrecorded timed AI on the breeding value estimations. And this is work that Flavio helped out quite a bit with. But what he saw was that in herds where there's 100% timed AI, everybody is using timed AI, the average breeding values that are estimated from that data are really quite a bit higher than those herds in which no timed AI is being used. And the problem is, nobody's writing this down. We don't have a record of that. LactaNet does a fantastic job holding the database for the national herd, but we don't have this information. How we did this is we just looked at herds and said anybody who's always breeding on a Thursday is probably using timed AI. And that's all we have. But when you see, this is a pretty clean simulation because Larry Schaefer helped out too, so I'm pretty sure they did good math as well. But this here represents the potential genetic gain that we lose because of our incorrect breeding values. So this is a thing. Like, we're making actually our cows that are not fertile look really good in a genetic sense, which is not so cool actually. Then Colin Lynch, who now works for LactaNet, a former PhD student of ours, together with the group again, he looked at real data. And this here, I don't know how many of you know about correlations, but this is a snowstorm, not a line, okay? This is the correlation between average breeding values estimated with heat detection, so actual biological expression of an estrus, And here we have average breeding values using timed AI. We would want this to be a straight line and all those little dots come together and line up, but it doesn't. So that means that animals who are ranked higher in one or the other scenarios wouldn't be ranked the same way using the other management system. So this is a problem, actually. What we should do, we think, is that we should probably include reproductive management data in our estimation systems. I'm not for or against timed AI, I just think we should write it down. So really, if we think about the true reproductive performance here that we talked about, we're not actually doing even this, as poor as it is, we're doing kind of this, right? And this is where Eddie gets all hot and bothered, because this is apparently not a good way to show a timed AI protocol. I'm sorry for that, but what I mean is that we're just masking the actual fertility of the animals with these timed AI protocols. So how do we do better? And anybody who's on the genetic evaluation board, there's nobody here who's on the GEB, will know that that's my motto. How can you do better, or we can do better? So we have to think about closer to biology fertility traits. And we started that collaborating with Ronaldo Seri from UBC, Augusto Maduera, he's now at Michigan State. There was a lot of work done with Audrey Martin as well, a former PhD student, where the veterinarians, they came up with this idea of size and position score of the uterine tract. And I need simple things to work with, so they gave us sort of 3 phenotypes. A size and position score of 1, where there's a kind of a high and tight reproductive tract, SPS 2, where it's a little further, deeper into the animal, and SPS 3, where it's a really deep, low set reproductive tract. So what they found was that the pregnancy per artificial insemination by size and position score was very different depending on the size and position score of the uterine tract. So animals with this type of uterine tract, they actually had higher pregnancies per AI. And our question was, okay, that's awesome. Can we estimate a heritability for that trait? And in fact, you can. This is some of the results from Audrey Martin's PhD thesis, where we looked at the expected heritability of this trait across lactations and within lactations. And you can see that even for a trait that's maybe not perfect, that's quite simplified, these heritabilities are still quite good. We can work with that. Another area of work was done also by Ronaldo and by Ella Dodd, a current PhD student with Flavio and myself. Shorter anogenital distance also has favorable correlations and with positive reproductive outcomes. So what is this? This is a trait that you can measure on the morphology of a cow. It's the distance from the anus to the clitoris. And then you can also make sort of assumptions about androgynous concentrations, ages at first conception, follicular recruitment, and pregnancies per insemination. Fantastic, right? We look again, as a geneticist, I like boil it down to one number, and that's heritability, if we can breed for something like this or not. And we can see the heritability of this trait is like 0.39. That's pretty high, actually. For a reproductive trait, it's super high. There's a lot of questions about this yet as to whether or not we can actually implement a system like this and how closely related is this trait with actual conception rates, but it's pretty promising. It's a lot more promising than age at first service, for which I might as well start trying to breed the farmer as opposed to the cows that he's breeding, right? Like, you might as well start selecting for age at first service in the producer themselves. But anyway, long story short, what we're seeing here is that these are viable traits that could be used in an actual program. There's also sensor data that can be used. These are standardized phenotypes based on automated sensors. We're looking and seeing that physiological factors affect estrus expression and embryo survival, and we're trying to find these genetic markers that show or that are associated with estrus expression and fertility. This is also work. We're looking at traits like days between calving and first estrus activity, because it's a lot easier to see through objective measures like an activity sensor. And what we see here as well is that there are some pretty good, strong heritabilities that we might be able to work with. And they're higher than the 0.02, 0.03 that we're used to, because they're a lot closer to the biology of the cow. The sort of more recent work started back with a number of Flavio's students, Paige Rocket and Ivan Campos, who started looking at heat stress, and now Ella Dodd has taken this work up, and her recently published paper on the effects of heat stress on first service to conception shows quite clearly that there are also differences in how animals feel and how they perform under heat stress. So here too, we can see that there's a threshold, that cows under timed AI protocols are actually more sensitive to heat stress. Their reproductive performance is more sensitive, and that many Canadian provinces actually do have high temperatures in the summer, and that is affecting also the ranking of our bulls. So super cool, interesting stuff. Now, I had already asked you as well about whether or not health traits could be genetic. We've been working quite a bit in this area together with our partners at Lactanet and CMEX. We have started this in sort of 2014. There was an influx of new traits coming in with mastitis resistance, metabolic disease resistance, hoof health. Most recently, Lactanet introduced the fertility disorders evaluation, or sub-index, I guess. And now, 2025, we're looking at these types of traits like respiratory disease, calf diarrhea, leukosis, and crampy. Now, here the heritabilities truly are low. And we've got some correlations between first and later lactations that are moderate, I would say. Cystic ovaries is a trait that kind of comes to mind when we're thinking about this, because when we look at this graph here, this shows in green the top-ranked bull, the daughters of the top-ranked bulls compared to the daughters of the bottom-ranked bulls for health traits, okay? The percentage of healthy lactations in the daughters of these bulls are on the y-axis, and what you can see is that there really truly are differences between the top-ranked bulls and the bottom-ranked bulls. Now, even if these heritabilities are admittedly super low, so if someone tells you genetics doesn't have anything to do with it, look at cystic ovaries. 95% of the daughters of highly ranked bulls have healthy lactations, and only 70 in terms of cystic ovaries in later lactations. The differences here are larger in later lactations as they are in heifers, but these are actually quite considerable differences in actual healthy daughters, which is really promising because it's not the be-all and end-all, but it's absolutely helping to create healthy herds. So keep these numbers in mind as well when you start thinking about fertility traits, because there is a genetic component to them, and it can be really useful as a tool to help healthy herds. Colin Lynch has done some really cool work on diarrhea and respiratory problems as well, looking at heritabilities there. The heritabilities here are quite low. Diarrhea 4% to 6%, and respiratory 3 to 7%, depending on the type of statistical model used. But what's super cool about this is that he's also begun to estimate heritabilities for infectivity and susceptibility. This was super hard to do because, again, we don't have a lot of data on this, but there's also work being done at the Roslin Institute in Edinburgh that sort of looks the same as our results. So this is really promising research because we can start to actually get down to the infectivity and the susceptibility of different calves. And again, Mike showed what the implications are of having unhealthy calves. If we can sort of create them with a little bit more resistance or resilience to these different pathogens that they have to deal with, then kudos to us. It's going to give our calves a little bit of a better approach to life. So here again, we can see the daughters of top 10% sires for respiratory problems and the daughters of top 10% sires for diarrhea incidents. There are differences there, even though this is really preliminary research. There's a lot of other work being done in health problems. Renee Bongers looked at leukosis. Gabriella Candello and the team have looked at crampy, hyperketonemia as well. That was a paper published last year where we've got heritabilities for these different types of problems. And I think it's really exciting. I mean, we work very closely between Flavio, Filippo, and myself and our team of students. This is really, people are sick of new traits, but at the same time, we can do our part as well to make sure that we've got great resistance and resilience to all of these different problems. One thing I wanted to mention, and I wasn't technically allowed to talk about inbreeding and genetic conditions, but I do want to mention Gabriella Candelo's work on genetic conditions, where we're looking at genetic conditions of detrimental homozygosity in the herds. If there's producers in the audience, please come and talk to us afterwards. Fill out our survey today about how you would prefer and what you think about actually reporting these problems on your farm, because what we've seen is that people feel really bad about it. And that's not cool, because if we want to do better, we have to understand what exactly is going on. So tell your friends. We don't have a good system right now in Canada for collecting information on detrimental genetics. I don't like to call it that, but they are genetic conditions. And with the increased use of these reproductive technologies and genomic selection, our train that we're on is going a lot faster. So genes and alleles spread a lot quicker in the population, and we need to make sure that we've got a good way of managing those. So come and talk to us afterwards if you'd like to know more about that. Ultimately, this research is super cool because it gets embedded almost directly into the lifetime performance index of our national herd. So we've already been able to see the work on the environmental impact that I didn't talk so much about, but we're hoping, we see here the fertility disorders have been implemented in the health index of Lactanet, and we're hoping that we can get some traction around calf health traits and novel fertility traits as well to improve the overall index, and then we've got some nice embedded tools to work with. Overall, I think genomic selection can help boost fertility and health. Novel phenotypes allow improved selection for important traits, but we have to really think carefully about the cost trade-off, right? What is the economic benefit of collecting these traits, because they're not the same traits as they were 10 years ago or 20 years ago. We've got new technologies, new ways of measuring things. We can't measure everything. We still have to be able to do it, but as Mike Coffey, a colleague at SRUC in Scotland, loves to say, in the age of the genotype, the phenotype is still the king. We still have to look at our cows. We can use all these new technologies, but we still have to know something about the physiology, the biology, and the morphology of our animals in order to best select the next generation. We need more data. We need to make sure that we are breeding for the right things, because it does work. You got to be careful what you wish for, because if you were on a path, you got to make sure this is actually what you want, because it will change. To Rupert Brookmeyer's point about short teats. Anyway, I want to say thank you to this wonderful, fantastic team that I have the privilege of working with. Flavio, my dear colleague, and Filippo. This wouldn't be possible without everyone on this team, past and present, as well as our funders and collaborators. And I got you like 6 minutes back. Thanks.